This is actually a surprisingly good turnout for polymorphic unions at 9 o'clock in the morning on the second to last day of the conference. So that's our topic today. So my name is Jason Lucas, and I'm not a real big fan of slides, so we're just going to be looking at code. This is kind of a codey subject, so we're just going to do it that way. So what we have here is a fairly simple, short class hierarchy describing two-dimensional shapes. I don't think there's anything here that requires all that much explanation. It's structure, but no behavior. So you're talking about just sort of object light. If we want to add various behaviors, we can look at doing that the C++ way. That is to say, we will put some pure virtual functions in the base class and start filling things in. The algorithms spread hither and yon throughout the entire code base. When we add virtual functions, everybody breaks until we fill them all in. Your diffs will sprawl over all the files in which these are implemented, which should be separate, one would think. It's hard to see the parallelisms and implementations between the various places where you're filling things in. If you have intermediate classes in the hierarchy between the most derived ones and the least derived, which this does not, those are going to group your behaviors in ways that are great for some of your virtual functions and maybe not so great for some of your other virtual functions, and that's just the way it rolls. But on the good side, the hierarchy remains open-ended, even across ABI boundaries. So if we want to add more classes or more more bits and pieces, we're free to do that. If we want to add more virtual functions, however, we can't. Right? Then we're going to have to recompile. So far, what it sounds like I'm selling you is this. This is the visitor pattern, which should be familiar by now, if only because of the number of people who have spoken out with great hatred for it. So visitor groups your concerns together. So, we have only one virtual function, which is the visitor acceptor. And then all of the algorithms group their bits together so they behave more like type switches. Your diffs are definitely more focused. So this is nice. We can work on individual algorithms. We've got a team of people. You can have people working on structural changes, which will require updates to all the algorithms, but at least the compiler can tell you. And when you have people working on the algorithms, they pretty much work in silos. The grouping of the leaf classes, the most derived classes, can vary from algorithm to algorithm. Behavior can change. So that's nice. We're not locked into the hierarchy in any particular way. And the hierarchy is sealed. We can't extend it across ABI boundaries, but we can add algorithms. So this is the opposite. We can extend the behaviors, but we can't extend the types. And the other kind of annoying thing about visitor is either you have to declare everything in an extremely specific order. If you notice, here we go. Where are you? The visitor is forward declared, and then all the finals are declared, and then we can define the visitor, and then we can define the visitor acceptors, and then we can define the algorithms. Or if you're not in the mood to do that, you can just sort of jumble it up, in which case everybody knows about everybody else, and you have poor isolation. And those are kind of your two choices. And either way, there's a lot of boilerplate code here. It's not particularly easy to read. Variant. We go back to our where we were with the first version. We've got nothing behavioral in the structures themselves. And then after we define all of these finals, we decide those guys collectively are a shape. Variant collects them post hoc into shape. And then we can define our behaviors like this. Looks a lot like visitor without the visitor. So it's much more terse. The algorithms have the advantage of being able to group the members of the union any way you like, just like visitor, except now we can use genericity to actually group them together into single handlers, which would be harder to do the other way. We're using overloaded lambdas here instead of explicit visitors. So it's nice and terse. And it's kind of nice that the right function can just be the insertion operator. So I think that's kind of nice. So I wanted to start with this example before we backed off into more abstract discussion of what variants are. So now that you've seen it, let me get a little more abstract about it. So boost says that a variant is a type-safe, generic, stack-based container offering a simple solution for manipulating an object from heterogeneous types in a uniform manner, whereas standard containers such as standard vector may be thought of as multi-value single type. Variant is multi-type single value. So I don't know why we have the rest of this hour to talk. That pretty much sums it up. We'll put this another way. The number of states a data structure can be in, it depends on what it's got inside of it. And in the case of a union, the number of states a union can be in is equal to the sum of the states that its members can be in, as opposed to a struct, where the number of states is equal to the product of the states that its members can be in. So if you talk to formal language people, they'll refer to this as a sum type, as opposed to a product type. Then they will talk to you about Haskell, and you should sprint away. So this will go by many names. You're going to hear it described as discriminated unions, tagged unions, sum types, variants. It's sometimes just lumped in with general type erasure, which it is. This is not a new idea. Alexandrescu kind of brought this to the public back in 2002 in Dr. Dobbs with a series of articles about discriminated unions. Friedman and Manon contributed the Boost variant to the Boost library at about the same time, shortly thereafter. And if you Google for discriminated unions or variants or any of those terms, you're going to find lots and lots of implementations. Still, it hasn't got a whole lot of traction. Why? I'm actually asking.
Because you see C++ programmers from a background where variant tests just aren't common at all. I think it's just all other languages they got things aren't very good at you guys are stuck in structs. It's a cultural thing. It's all
Oh, interesting. Maybe, but we have. I mean, C++, revolves around its class hierarchy. So saying that C++ doesn't have this kind of polymorphism, it's true, but C++ has polymorphism. And what I'd like to demonstrate today is that a union is actually a class hierarchy collapsed into a value type. It's exactly the same polymorphic behavior. It's just nicer in some respects to work with. There's what I think has been an issue has been that the Boost implementation was suffering from having been written in 2003, when we didn't have a bunch of language features that we didn't have lambdas, we didn't have R-value semantics, we didn't R-value references rather, we didn't have variadic templates. Basically, trying to do this with the 98 standard was like going to the moon with stone knives and bear skins. So The boost one also made another choice, which is something called the never empty guarantee. If we have this union of circle and triangle and square, what happens if we default construct?
Okay.
Well, that depends on who you ask. What is the correct thing to do? Alexandrescu's implementation would default construct an instance of whatever the first type was, otherwise known as surprise. It's unclear what the correct thing to do is. It's also, therefore, unclear what to do when you have a moved out variant. If I move from a variant to another one, what am I left with? So the implementation that I'm going to show you today, which was written by me and my colleague here, Michael Park, wave, there's Mike. We decided that the never null guarantee, never empty guarantee, is nice sometimes, and sometimes it's a pain. So what we did was say that the variant, if it includes a null type in its list, then it's allowed to be null. If it doesn't, then it's not. So, and we have some enable if voodoo in the definition so that certain things are not there if it's not allowed to be null. So it won't default construct. Wake up. Okay. All better. It won't default construct. It doesn't have a reset method. If it can be null, then it has operator bool cast defined, so you can test it for nullness. In other words, if it can be null, then it behaves almost exactly the same as a pointer to a base class. And you do everything you normally do with it, except that it's a value type. So the code that we're going to show you today is on GitHub. Feel free to go there and play with it. I don't think what you have today is, as it stands, a strong candidate for the standard library, but I kind of hope that the standard library will have a variant. And if you like some of the semantics of this one, then we can talk about maybe moving this thing towards some kind of a standard. So I want to take a little bit of time and walk through how this is actually implemented, because I think demystifying these kinds of type erasure containers is a worthwhile thing. So in this case, future-proofing, pull in some stuff that's going to be this way shortly anyway, and that this compiler just doesn't happen to do. It's not very interesting. Anybody need to go over this stuff? If you see something on the screen, then you're not sure what it is, just put your hand in the air. All right, so here's where we get into the thing. This is the type that we use to say if this is included in the list of parameters for the variant, then this is a nullable variant. We actually had null pointer t here. I still kind of think maybe it should be null pointer t. Mike doesn't, so he got the last edit on this file, so he won. Yes, we are secretly using the visitor pattern. It's really not a secret. You should have been able to see that. But the visitor is being defined with variadics with a recursive pattern here. Again, this isn't totally surprising. And then this is overloaded macro, or overloaded lambda rather, which, what, did I skip it? Okay, where are you? All right. This is actually a little harder position than I was hoping for. So this is overloaded lambda. So did you know you could inherit from lambda? And even a variadic list of lambdas. So the result is a function object with operator paren defined for all these overloads. And then if we then have a dispatcher that can bridge us from variance pure virtual dispatch to one of these things, we're golden. And that's basically what we're about to do. So variant itself, okay, so a little bit of preamble, a little bit of...
Can I ask you a question?
Sure.
What, if you can do the lambda thing, what are you using the visitor for, actually?
I'll show you. So if we can, the question is if we can do overloaded lambda, why do we need the visitor? The short answer is we have erased the type. So we're going to need to do a runtime type check to know what to do. But you'll see it's a little more clear in a minute. So,
One more question.
yep.
It's a little bit easier to read if you don't have the minimap on. Just
Which one?
if you don't have the minimap on the right on.
Oh,
Spelling out stuff, that's all.
yeah, I guess so. I'm afraid I'm going to have navigation problems without it. Let me see how it goes. I can turn it off. And the code is actually on GitHub, so right this second. So if you just go to github.com, jsnl9000, CPP14, or CppCon 14, you'll see everything. You can just follow along. Anyway, so variant is a variadic template. It has a little bit of preamble stuff going on here for deciding a few things. Some basic stuff like a union of nothing is not fair. Don't do that to me. Define our visitor, and then you'll see here the default constructor is available if we have null in our list. Otherwise, it's not. And then you'll see the actual trick. And I'm not going to get too much into this. If you're really interested, go read Alexandrescu's articles because he spent 3 issues going through this in extremely hairy detail. But the basic idea is we're going to create a poor man's virtual table. So that's what this tag data structure is. And this is when we talk about a tagged union, we mean that the union has some kind of piece of data following it around that says what's currently in it. And in our case, the way we do that is with an instance of, come on, this data structure. So it's a data structure full of pointers to functions. And in other words, it's a vtable. So the constructor functions that we use for it, getTag, is templatized. getTag has a static constant instance of it and just fills it up with some lambdas that do our work for us. There's also the null version, which doesn't actually do very much. And then here is our tag, and here is our storage. So all we have is a blob of bytes that is big enough to hold the largest thing and aligned to whatever the strictest alignment is in the set of types. And then if you look inside of these guys, they work with that to do whatever needs to be done after going through the virtual dispatch to get this far. So this is where the type erasure kicks in, or the unerasure in this case, the type reveal. And these guys are used to force the blob of bytes to behave as whatever type the tag discovered they really were. So you can go through here. It's probably exactly as you expect at this point. The destructor for variant hands off to the destructor here. The copy for variant hands off to the copy here. All of that stuff. So at that point, we're kind of done with variant. And the rest of this is all of the stuff, and this is one I'm not going to get too terribly into because it is a little bit more template magic-y. How to define this visitor for us automatically that will dispatch from the virtual entry points to whatever the functor object has that matches us for an overload. Magic going on. I'm happy to sit with anybody later after the talk that would like to know more about exactly how this part of it works. But the practical part that you need to understand, or would be useful to understand, is that when we accept a visitor, where is accept? Come on. Where are you? Get type info, accept should be above that. Variant, all right. Yeah. There it is. When we accept a visitor, we ask the tag to do our accepting for us. We pass the information through. Once we're inside of tag, we have the right information to dispatch to the correct overload of operator pren in the visitor object, which is a pure virtual, and then it jumps into that big complicated applier thing, which hands off to the functor object, which is the overloaded lambda. So there's a lot of extra dispatch going on. We're going to talk about performance later, as I just heard everyone in this room think out loud. So any questions about variant before we move on, the actual implementation? Oh, good. I knew that was going to be simple. So why would you do this? So I have a few things I would like to talk you into today. Variants can be more flexible than hierarchies. Variants can be easier to maintain than hierarchies. A variant with a null state is like a superset of optional. Variants can do dispatch tricks that you simply cannot do almost any other way in C++. And it gets you out of a lot of complicated situations, a few of which I'll talk about. So getting back to the top of this, variants more flexible than hierarchies. We talked about how intermediate classes in the I'm sorry, go ahead.
I just had a question about flexibility. So in the previous slide, you showed the various methods, and then it was kind of a set of lambdas for each one. And I was wondering, if you add a new type to your variant, is there a way to define those methods for that type separately, or do they have to be all lumped together?
So the question is, when we're defining behaviors, if someone comes along and adds something to the union, which means the union type is changing, do all of the behaviors break, or can we handle the addition separately? And the answer is it depends. What I'm about to show you is that you can go back to generics inside your handlers so that you can get multiple kinds of dispatch going on within a behavior, so that you might be agnostic about a lot of changes to the union's membership. If it's not, then you get an error that says something along the lines of, this case isn't handled here. So it's not a terrible error, and it's essentially the same error as, I can't instantiate this object because there is a pure virtual in it. So you're not actually any worse off this way, I think. And you have at least a chance to do better.
So does it mean that none of the types are convertible to each other?
No, they can be convertible to each other.
You still get the error message?
That's what I'm about to explain. So I talked earlier about the idea of, if you have intermediate classes in your hierarchy, by the way, I woke up today with a cold. This is a little rough. Please excuse my voice. The groupings of the intermediate classes might work well for certain behaviors and not so good for other behaviors. One of the ways in which class hierarchies are classically brittle is that they're designed around some set of behaviors, and then new behaviors come, and it's just not well laid out for them. Or, and this happened to me while I was working on MSIL at Microsoft, we had two perfectly good ways to lay out the class hierarchy, depending on which set of functions were your favorite. So if you have that situation, you choose one or the other, it's almost always the wrong thing to do. You should really choose neither of them or both of them, but favoring one over the other for no particular reason just will eventually bite you. The problem is, when you need to do that, you need to now talk about virtual inheritance and establishing diamonds in order to not favor one over the other. And that just gets horrible. So dispatch goes down in terms of efficiency, and it becomes hard to maintain. You can't do complicated constructors very easily. It's just a mess. So in this case, what you can do is, in your overloaded lambda, you can choose to use generics, or possibly even concepts, to group your handlers such that they will handle the members of the union differently. For example, my pointer. So we have some simple ones. And here I'm suggesting that these are actually in separate header files, because this would be the way you would roll in a large project, so that you could work on your finals as separate modules with their own unit tests. All of their stuff belongs to them, and they don't know anything about each other. So we've got dog, we've got cat, we've got horse, and then we decide to make animal. Animal depends on them, and then creates the union. And we could add behaviors now about how we like to group virtual behaviors out of animals. So animals all make sounds, animals all interact with people. How we group these classes to do that would depend. So we might have, like, we want to deal with the dog and the cat together as house pets, and the horse separately for some things because it's big. We might want to group the dog and the horse together for some things because we like them, and the cat separately because we don't like the cat. So the individual algorithm decides how it wants to handle things by creating its own generic projections at that point. Okay? So that was what I meant by variants can be more flexible than hierarchies. Variants can be easier to maintain than hierarchies. As I said, you build all your final types first, just like this. They don't know about each other. They don't share concerns. Your designs flow from the specific to the general instead of the other way around, right? When you're designing a class hierarchy, you start with this most general thing, and you start drilling down to the specifics. And you might not know very much about the general when you start. And you may change your mind later about what the generalities really are. And kind of like jacking up the entire class hierarchy isn't any fun. Yep.
When you were talking about, sorry, to skip back to the algorithm grouping things differently, what mechanism without concepts would you use to actually make the groupings? I mean, would you?
Well, templates are great. So we can use abstract lambda. We can use generic lambda, rather. So for example, the mechanism, the question is about how you use the mechanism of the lambda to do the groupings. So the simplest case is use auto. Basically, you've written default. Right? If you do have hierarchy, membership, they can be nothing but tags. Right? The type is transparently convertible into a group. You can add it later. It does nothing. It doesn't hurt you. And then you can behave off of those if you wish. You can also, it's also possible to use estimate. If we look up something in the dependent scope, and then we will either specialize or not. So, or instantiate or not, rather, sorry. But that's a little trickier. I'm not sure. You would do that, for example, if you're super interested in job security.
I think concepts would be the nicest way.
Well, that's why concepts are coming, so we can do stuff like this. And it does, we've tried that, and it does work pretty well. So, easier to maintain. Working from the specific to the general also grounds your initial work in the problem space most of the time, right? Dog, cat, and horse are things. We can compare them to real things in the real problem space and decide if this is a good representation of a dog or a cat or a horse. And then when we move toward the abstract, we do it by collection. It's better match for the way human brains generally work by cognitive clustering. It's also possible to do this. So here we have car and plane and horse, and we collect them into transport. The same idea, except that's the same horse. So this is the equivalent of multiple inheritance without the possibility of the class hierarchies poisoning each other. Right? Nothing is leaking back and forth. the horse is horse, of course. In design the whole talk around that line. In either case, and it would be possible even to do a transfer from one, and this is something we'll show you possibly later if we have time. It's a runtime type check to move from one variant family to another if they have states in common. If you're moving from a subset to a superset, it's not even a runtime type check. That's just okay. If they don't have states in common, then it's a static error because it's clear that that assignment would never make sense. So it's much easier to work with these guys where horse or whatever your final types are being reused in various groupings than to try to figure out how to make virtual base classes work properly in multiple inheritance, I think. So I've said a couple of times that if you use the null state, this behaves, the semantics are virtually identical to carrying around a base pointer into the class hierarchy. So if I can have car or plane or horse or nothing, then I'm actually, it's like this is transport star. And you just have to have one additional handler in all of your algorithms for the null case. You can also check for the null explicitly because we added methods to the interface of variant that only show up when null is there. The difference is this is a value type. So you're not carrying around a base pointer. You're not doing a heap allocation. Right? You're not, in general, doing anything that's involving indirecting. It's a value type. It just has the semantics of a base pointer. So if we have this possibly nothing state, then the simplest case is we have something or nothing. So we could have a template of variant where variant is t or nothing, which would be optional. It has basically all the same semantics as optional. It's just a little bit more general. So we could be a t or a u or nothing, for example. In the case where we are bool or nothing, then we are actually tri-state bool, where you can interpret the nothing as I don't know, for example. And we could overload and or and not to give you tri-state logic that works across this perfectly well. And because we know null isn't the same null across all the different unions, then we could do comparisons that give rise to tri-state bools that just work. And so for example, if we're using optional int, that's the same as a database nullable field. So we pull in someone's age from the database, maybe we don't know it, we get optional int or nothing. And then we compare it to some number, we get optional bool, and we can then do that with an and of some other comparison where we get another optional bool, and it all just sort of percolates up and it just works. And then, of course, when you actually try to use that in an if or a while, you get the wrong type. But at the top, you have to check what it really is. The boost version of variant explicitly doesn't do this. They said if you want to be null, you should define your own null. I didn't really like that very much. I think having a single definition of null enables what I just described with the contagiousness of null when you're doing operations across multiple nullable types. Another interesting pointer, by the way, is if we replace null with an exception pointer, so it's t or exception pointer, then this is another Alexandrescu special, expects. So we can implement expects as a variant, and it just works. I generally think it would be better to implement these guys as variants rather than re-implement the base type erasure behavior over and over. So on to the next trick. So let's go back to our shape example. I like shape. I want a function. It takes two shapes, returns bool. True or false, do these two shapes intersect? Can anybody immediately see why this problem sucks? Yeah. So intersecting a circle with a circle is easy, or a circle with a square, or a circle with a triangle, or a square with a triangle, or as long as you know what both of them are, we know what to do. But we have to know what both of them are. Being polymorphic on one of the shapes still leaves us with a damn shape that we don't know what it is. So this in general is the multi-method problem. And there are a handful of languages that solve this tidily for you. OCaml, Celos, end of list, I think. C++, not so much. This is one of the prettiest things I've ever seen. So you can dispatch multi-method on variant. So we will be polymorphic on more than one thing. Instead of having a this, you have an array of these. And we will work out what all of the types are of all of these before we dispatch to the correct handler. And this is another case where you can generally collapse a lot of cases, because intersecting left circle with right square is the same as intersecting right circle with left square. That kind of stuff. So you don't actually wind up n squared most of the time. But it's nice that you can, and the entire algorithm is right in front of you. All of the dispatch machinery is just locked away inside of variant. And you never have to see it. So I just kind of like to soak that one in for a minute because I think it's beautiful.
Do you do arbitrary, do you do just two arguments, or?
No, I'm glad you asked. The question is, are we limited to arity 2? No, you can go as far as you want. In practice, arity 1, common, arity 2, common, and then there is a sharp decline. And let me explain. This whole thing comes up because I'm a compiler guy, and when I'm trying to figure out the type of an infix operation, and I need to know the type, it's based on the types of both sides, I use one of these. It's so good. The number of ternary operators in C is small, and the dependence of the output type actually doesn't care about the first one.
Right.
So we're hard-pressed to actually come up with a true ternary operator where all three types matter. It's possible. There are cases, I bet. But one thing that would be interesting to note here is this is shape. You don't actually have to be homogeneously multi-method. If you need to take your animal for a ride, we need to know about your transport and your animal at the same time. So this is Mike's example. I think it's really cute. Any of these cases, we have problems. Horse won't fit in the car. We can't put the animal in the plane. Putting a horse on a horse is dumb. And that's possible because horse is in both, right? And everything else is fine. And the auto just eats the other cases. I think that's really sexy. So
you need C++ 14 for this, right?
this code uses C++ 14, requires C++ 14. For a very small number of things, we could do without. In particular, when we're doing the apply inside of the applier, the thing that inherits from the visitor and does the dispatch, we use tuple apply in order to unwind the thing, which uses the trick where we're going to expand a parameter pack of integer indices. So, you know, the index sequence stuff that's in 14. But you can write that in 11. It just didn't make it into the standard library. just like we're using some 17 things in this header, you know, we could make this whole thing work with 11 very easily. I just,
Except that part.
hmm?
Except that part. Except that.
Yeah. But the way this works, there are a few cases where you might not want to use overloaded lambda anyway, where you have a functor object that does more stuff. That entry point is actually still here. So if you just want to define your own functor and fly, or if you really want to use your own visitor, you can. The dispatch is the same. So one cautionary note about multi-dispatch. This is not the fastest horse in the plane. You are going through multiple levels of dispatch in order to unwind this operation. As we discover what type is on the left, we cache a reference to it, discover the next one, cache a reference to it, build up a tuple of references to everything, and then eventually push it through. It's a lot of steps. So in general, this kind of dispatch is no faster than half as fast as a virtual function. And in general is somewhat worse than that. However, if you turn on like full boogie optimization, whole program optimization, devirtualizing, in a lot of cases we know what these types are, so the first level of devirtualization goes away, or the first level of virtual function goes away. So it's not horrible. This is not what you would do in the tightest of loops, where you have extremely tight performance considerations. All right. So when do we do all this stuff? Why would we use a variant? So have you ever tried to create a pure virtual templatized function? Boy, that would be nice, wouldn't it? Of course, we can't do that because the vtable needs to be a finite size. So the trick is that we use a virtual function, but we pass unions, variants, or we return variants, or both. So we solve the genericity first, right, by taking whatever the type is, stuffing it into something that makes it homogeneous, and then we dispatch polymorphically on that, and on the other side, we visit it with a functor. So you can, for example, create meta-access functions for your data structures to say, like, I want to access a field by name at runtime, like the cool kids over in Javatown. You can do that. We don't know what the type of the field is, so we'll have to return you some kind of a union. We can take a regular container and turn it into a generic container by having it contain unions. For example, what's the difference between a vector of unions or a tuple? Ordering. So what's the difference between a map of string to union and struct? Thank you. Yeah, so speed. The tuple and the struct are resolved statically. We're going to resolve some things dynamically in the case of the containers full of unions. But you get, something a little closer to what a scripting language can do. It's not always what you want to do. We're C++, we're a systems programming language, but it's nice to be able to do scripty things without having to bleed out the eyes for it like everything else we do in C++. So in this case, for example, if I have a config file, I can read in my config file very straightforwardly, make a dictionary, a mapping of named values to unions of their possible actual states, and just fly with it. All right, so it's really handy for processing things from the outside world. It's also handy when you're going over a string-based interface, a string-based API like a REST interface, because we're going to parse a bunch of stuff find out what the types are, and then stuff it all away into some kind of container that associates the values with their names, and dispatch it into a handler that will worry about it all later. So this is handy. In general, you can do this anywhere you want to do type erasure, anywhere you would use any. Any is, I would say any is more than type erasure. Any is type obliteration. Any is almost a void star. So I think of union as please step away from the void star. Think about it, decide what your finite universe of types really is, and then use a union instead of just leaving the entire universe open with any. Now, there are a few cases where you really do have an infinite universe of types. By all means, use any. But most of the time, you don't. So I think variant deserves more love. I think it's a good model for future-proofing your code, because when we make the changes in 17 or 20, where the build model will change, and we'll be able to do whole program compilation and things like partial classes, then this jazz becomes real vtable, right? Because I can take type switches, and as I reassemble the whole program, I can put all the pieces together and make one big vtable out of it. So right now, this costs you extra dispatch. Right now, this is a convenience to the programmer that costs you runtime. When we change the build model, that might not be the case anymore. So, it's all right. I'm done. It makes your projects easier to design, easier to maintain. It does sophisticated tricks like multi-method while remaining very terse and very readable. Our implementation is certainly not the only possible one, but it's short. And I think we wrote it so that it was actually be comprehensible. By which I mean it's not written like anything in Boost. Okay, I'm done. I'm not gonna be mean to Boost now. That need to be backward compatible to the universe and portable and everything. It's just like makes code really hard to read, I think. This isn't like that. So even if this particular implementation is purely a teaching experience and you guys go implement your own and until the standard one comes out, I still think it's a useful idea. So anyway, that's kind of it. Questions?
What's that GitHub reference again?
GitHub, JSON L9000 / CppCon 14.
You just search GitHub for CppCon 14. There's only 3 things. You'll find it.
So, on the performance issue, if I implement,
I knew it.
if I implement a sort of variant-based design and I discover that I wind up having a multi-dispatch inside a hot loop or something like that.
Mm-hmm.
Do I have any sort of localized options for improving the performance of that without tearing apart my whole design?
Yeah, you can fall back to what we do with any, which is go fish. There's a try-as interface on variant. Mm-hmm. Thank you. Where you can say like, well, if this one actually is a string, then I'm just going to nab it and go off and do stuff. So you can early resolve the type. There's another thing too. The lambdas don't have to be short. And by short, I don't mean lexically short. I mean their stacks don't have to be short. So once you resolve what the type is, you can then go jump into a whole separate module, a whole separate library that just deals with dog or just deals with horse, and the virtual dispatch is over. Right. The other thing we're not showing here is it doesn't have to be a constant reference. You can have a mutating visitor. So that's really comes up when you do have long-lived visitation. So, and at that point, you're really absolutely no worse off than any other technique. You paid the price exactly once.
Great, thanks.
Mm-hmm. Yes, sir.
You're talking about parsing like a config file or something.
Mm-hmm.
What about like recursive variants?
Uh-huh. So Boost uses a separate type for recursive variance. Sort of the poster child for this is expression. So infix is a kind of expression, and expression is a union of a bunch of other things, including infix. And infix has two expressions in it, left child, right child. So we solve this by going back to recognizing that the union with a nullable in it is the same as a base pointer. So what we aggregate in infix is pointer to expression, right? And we can have a forward declaration of expression at that point that we finalize eventually with the union. So exactly the same thing you would do if it weren't a union.
Do you have use examples in this GitHub?
Yeah, we do. In fact, so my backup slide, if I had slides, here's an entire language interpreter written with, yeah, simple calculator, written with a union for values and a union for expressions. And it actually works. So, and it's actually pretty short considering. Yeah, well, I didn't have as much time before this conference as I thought I was going to have. I try to remember to go in and comment things, and so I leave nag messages for myself. So, for example, sir?
Yeah, I have a question. If is it possible to sort by type? I mean, I want to deal with all the dogs at once and all the cats at once and all the...
Yes. So you can define, for example, a strict weak ordering operator like less than on variant, and then decide that all dogs come before all cats come before all horses, and then among dogs you sort by breed or whatever. So you can impose all kinds of collective behavior.
Thank you.
Sure.
I'm not very familiar with the libraries but are there, like these, you talked about type indexed. So are there tag indexed unions?
Are there, you need to speak up a little.
Are there tag indexed unions instead of type?
The question is, are there tag indexed unions instead of type indexed unions? I don't know what I'm not sure I understand.
Okay, so for these, when you construct a union, you don't write any, for example, like if you got a dog and a horse, right? You choose the type of the dog, what's the type of the horse, determine which one you choose.
At construction time.
At construction time, yes.
Mhm.
But in a tag base, you give them a name and say, you know what, I want left and right, both of those are dogs. A tag, like just a name for things. Type.
If they have a default constructor, it would be possible to do that. The problem is I need some state to copy or steal to initialize the variant. So if you create a dog as an R-value reference, I can move it, and then it's my variant dog. If you just say, I want a dog by name, then I need some kind of a factory. So we could build a factory pattern around this as well. It would just be something that sits on top. It wouldn't really change this at all. I can talk to you about it afterward if you like. Anybody else? I think, oh, okay.
The example shows is a match on two arguments. So is that kind of symmetric where like multi-methods where you don't get a preference over, or does it work more like pattern matching where you just go in that order and try the first match?
The question is whether it works like pattern matching and is therefore not order dependent. It is not order dependent, it works like pattern matching.
So, but you also had in the example of like car, plane, and animals, you had like unless I got it wrong, like you had the animal in the first argument.
Mm-hmm.
Like so, why should that be excluded by type checking? Was I right that there was like an example where it was in the wrong position?
Oh, it wasn't in the wrong position. We were showing that you can do multi-method dispatch across heterogeneous sets of variants. So,
yes, one was the variant of animals and another was the variant of
transports.
transportation,
Right. It was kind of a, not a very meaningful example per se, but the point was they can be
But
different.
it means I can stick an animal into the position where the variant of transportation is.
Only horse. The example, right, because Horace lived in both unions. So you can't violate the type rules. It is still strictly type safe.
So is this also based on the types have to be the same where you look, or like can they be in some sort of subtype relation, like convertible or something?
You can actually mix inheritance and unions. It's doable. The point is, sometimes you're going to do inheritance for classification, for behavior, and sometimes you're going to do it for construction of the type. Basically, it's a form of aggregation. So you're going to stick things in, but not be them for the purpose of an algorithm. That's fine. You can certainly do that. And then those bases later you could match on, if you wanted to, with an overloaded lambda. But you could do the overloaded lambda on anything that would be statically discernibly different about the type.
The overloaded lambda it's just like overload resolution, right? So you can use type conversions and so forth in the same place as you could with an ordinary overload?
Absolutely. So, for example, the right, like I want to stream this variant out, the simplest case, right? You just have a single auto that whatever it is, I shove it onto an outstream, and it's fine, right? Because they all provide their own overloads for doing that. But then you could also use binding strength rules and say, well, in general, I'm going to output them this way, but if this is dog, I'm going to do it some other way, right? So you have the option to break out of the default behavior any way you want.
Okay, so also, I didn't see quite the performance, like if we are not talking about like dispatch on several arguments, but just one, so kind of what people typically would do with virtual functions or visitors and pattern, if they go like, so what's the heat this will get you? Like what's the performance in comparison to just using virtual functions?
It's no faster than 1/2 as fast as a virtual function. And some of my examples actually were going...
Slower.
It is slower than a virtual function.
Yeah, but
It is between half as, and in some of my cases, 1/6 as fast as a virtual function. But it's not 100 times slower than a virtual function. It's not a different world of badness. It's okay. And actually, I'm not even sure why that 6 happened. We were messing around with some of the performance testing, and it was kind of jittery. So these are not numbers that I necessarily stand by, but we are close to not quite as bad as half as good.
Have you also measured like how much memory you would given like a variant of like m to dispatch like on k arguments? How much memory would you need like to generate the v tables or like any underlying data structures?
The intermediate applier data structures are tiny. You're pushing stack frames in order to resolve. So you've got stack frame size, and you've got a little intermediate object that's done as a local. It's not very much.
So one thing I'll mention is the end visitation, arbitrary visitation, was more of an academic exercise for me to generalize it to n, because as Jason said, like going past 2 is very impractical, it's very uncommon, and so it's an exercise for me, but we haven't actually done much enough analysis on visitation.
So I think we're officially out of time. Thank you all for coming. I hope you play around with variant, and feel free to grab me if you have questions.